Alright, so imagine you've been put in charge of organizing a fishing tournament, and we need to get their weight. So that we figured the best way to measure the length, or get their weight, is by measuring the length and using that. And we have this data to start from. Graph the scatter plot of this data. Is the data linear? How can we tell? So we put it in our lists, stat plot, L1 and L2, we get a graph, and that doesn't look very linear. It has a curved kind of pattern. You could argue it's linear, but I think it's pretty clear it's curved. So also we want to do linear regression. So we have our A and B, our R squared and our R. R value is not bad. 0.94, 0.95, we round it. Not bad. But our graph didn't look linear. So we look at the same thing here, Control I to get a new page, data and statistics, length versus width, and we have this curve pattern yet again. And we can just do our regression right on here. We can't get our R value that way, so Control I, calculator page, statistics, stat calculations, and linear regression A plus BX. So that's the form we've been using. So it's length and width. So we get our R value, it's the same thing as before. So it looks like it's a decent linear model, however it looks like it's curved as well. So how can we tell if it's actually linear? We have to do a residual plot. Now here, once you do your linear regression, click on Analyze, Regression, or Residuals, and show residual plot. And we can see that there's definitely a pattern here, and there should not be in our residual plot. There's a curved pattern. You can kind of see it here as well, but it's definitely pronounced here. If we're doing that on the calculator, or the 84 I should say, we need to do the linear regression, and then when we go to stat plot, instead of L2 we're going to plot our residuals, which if you go to second list, it's at the bottom here. We graph that, and you can definitely see a pattern. And it shouldn't be. We should have no pattern. So, linear model is probably not the best for this. Is it linear? No. Because the residual plot has a pattern. So it's not linear, even though R is 0.94, which is a pretty strong linear positive relationship. It's still not linear because the residual plot shows that there's a pattern. So maybe there's something better. This section talks about transformations so that we can straighten out nonlinear patterns and make it linear. When you buy pizza, you order it by the diameter. However, you get more pizza or you measure how much pizza you're actually getting by area. So this is just a little formula showing it. Our diameter is x divided by 2 is our radius, so radius squared, square it up. So it's a squared relationship or a quadratic relationship. Now the power model is y equals ax to some p, some exponent. In this case it's 2, and a, our constant, was n over 4, or pi over 4, should say. Other relationships that we could see, distance an object is dropped from a given height is also quadratic. Distance equals some constant times time squared. As it gets faster, it gets exponentially farther away. The time it takes a pendulum to complete one back and forth swing, its period, is related to its length by the model. Period equals a constant times the square root of the length, or the length to the 1/2 power. So P would equal 1/2 here. The intensity of a light bulb is related to distance from A over distance squared, or distance to the -2. So P equals -2. So there's still all these powers. So let's go back to our fish data. Length is one-dimensional, but weight, like volume, is three-dimensional. A power model of the form weight equals A times length cubed should describe the relationship. What happens if we cube the lengths in the data table and then graph the weight versus length? So we're going to change length to length cubed, because length cubed will give us our weight, give or take, kind of like volume. So if we're on the 84, go back to our list, and in L3, we don't want to change anything, or any of list 1 or 2, arrow up to L3, hit enter, and then we're going to do L1 cubed. So second stat, L1, the caret key cubed. And then what that's going to do is going to cube all the x values here, and we're going to graph that versus our y values, the weight. So we go up to stat plot, go here. So now instead of, first of all, our y list, we want back to L2. And our x list, we want L3. We want our cubed length. Now when we graph it, I probably need to do zoom, stat. Now it looks a little bit more linear. And if we do a linear regression, now we're going to do it with L3 as our x, and then L2 as our y, just like it was before. We're not changing the weight. Now we have an R value that's 0.997, much closer. And if we go back here, and instead of L2 putting in our residuals again to get our residual plot, let's zoom stat again. There's no pattern there. So that is linear when we cube it, because we have that cubic relationship. But now we can do the same thing here. Now I've already graphed this. Let's go back. Menu, analyze. Alright, so I've already run my linear regression. Just off my analyze regression, did linear, the A plus BX. So now I do residuals, show residual plot. And again, this is our curved pattern. We don't want that. So we go back here, equals L cubed. That is our variable reference. The same thing that we did on the other one, we need to label that. So cube. And then we're going to graph that. So we'll go back to here, and instead of L, we just click on cube. And it fixes it automatically. Look how close it is to this line now. No pattern here. Not a very distinct pattern anyways. So this is linear. And we can just arrow up. No, we can't do that. So menu, statistics, stat calculations, A plus BX. It is our cube is what we labeled it, the length cubed, then the weight, and we got the same R value. Our R squared value is also very good. 99.5% of our predicted Y values are explained by the line. So it's a very good line. It works out. Yep. So does the data appear to be linear now? Yes. And why is that? We need to explain. The residual plot has no distinct pattern. And you might say there's somewhat of a pattern, but it's not a distinct one. There's no curve like we saw before. Linear correlation coefficient now is 9976, so much better. So what is the least squares regression line? Well, it's our predicted weight we have to find our A and B. We have our A here, we have our B here. However, our X value is actually length cubed now. That's what we put it in as. And we can see A and B, the same thing here. So, what is our line? Well, our y-intercept is 4.066 plus our slope, and it's times length cubed. So a little bit different. Now suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. Use the least squares regression line to predict the weight. So we just substitute it in there. Our predicted weight is going to be that. When we calculate it all out, it's about 688.855 grams. That's our predicted weight for this 36 centimeter long rockfish. Now, instead of cubing the length, we could have done basically the same thing and taken the cube root of the weight. And you can see that this is a linear pattern as well. A little bit better. Here's our data that goes with it. This is our length cubed. This is our cubed root of weight. So we did it to the y value instead of the x. And you notice that this one's actually a little bit better because our r squared is 99.8 as opposed to 99.5. We still have our A and B. We have length here, but we have length cubed here, but it does say what transformation happened. And you can see that both residual plots are linear. So we don't have to worry too much about that. So when experience or theory suggests that the relationship between two variables is described by a power model, you have two strategies for transforming the data. You can either raise the x value to the power, or you can take the pth root of the values of the response variable. So you can do both. This one's probably easier because we don't have to have square roots, cubed roots, fourth roots, anything like that. We just raise it to a power so the numbers get bigger, but both will work. If you have no idea what power to choose, guess. Keep trying different stuff. It's not very difficult to change it. We just go back here and change it to 4 and see. So then if we went back to our graph, well, that doesn't look very good. So we know that's probably not the right one. So we're looking at all those different things. And that's what we need to get out of this. That sometimes we cube it, or we raise it to a power. Sometimes we take the root of that same thing, depending on what it is. Area squared, volume, three-dimensional, cubed, or cubed root. We saw pendulum is to the 1/2 or the square root. Intensity and distance of a light bulb is to the -2nd, and sometimes they'll just give it to you. So that's what we're looking at. We're trying and find some transformations that work and answer some questions based on those.